course.
Oh, thanks,
I can, but it's his. I was just riffing off of his solution, so.
It's true.
And by all means, go ahead.
I am recording this, so Kevin, why don't you go ahead and do that?
All right.
Just share your screen and walk us through the changes.
All right. Can you see my screen?
Thank you.
Yep.
So, as the function signature, I take in a node, just going to be the root, and the first if statement, I check if there is a left node, and if there is, I then check if there's a right node, and if there are both nodes are there, then I return an array of the highest value of between the nodes. I make the recursive call in here, taking in those nodes. And then this statement is if there isn't a right node, just a left, then I only call it on the left node. And because we accounted for the left and the right here, this would only hit if there isn't a left. So again, we check if there's a right, make the function call, and then else if none of those hit, then there is no left and no right. So we just return the value. And I kind of wrote down what happens here, but yeah.
Cool. Liana, did you have something similar or different?
Different.
Cool.
I just, where is it? Hold on. Where is it? There it is, I think. Can you see my screen?
Mm-hmm.
Yeah.
Okay. All I did was make your left max and your right max optionals instead of setting them to initialized int. And then I force unwrap them because we're checking in the if let statement if there is a left child to the root. So if it is, it will put a value into left max and into right max.
And why don't you get a crash at 338? Because you're forced unwrapping something.
Well, I guess if you mean with left max and with right max?
Yeah.
Because we're checking in the if let if there's something there. If there is a value in the left child of the then root, and that is the only time when we set left max and right max.
Okay. So you might be forced unwrapping nil because you might have no left max or no right max, but there is something else you do in your code to make sure that you never get to that step.
Sorry, say that again.
So like left max and right max, if you never, give me one sec. Oh, that's something. Has anyone seen the baby monitor? Sorry. So left max and right max, if the optional binding in 330 and 334 does not work, you might have left max and right max still as only those optional ints that were never initialized. However, what point in your code makes sure that doesn't happen? Where do you protect against that?
At the guard statement?
Yeah. Tight. Sweet.
Right.
Hi, Tia.
Hey, y'all.
Tia, you're the one who's on the record now. Did you do the lab?
This is for the binary tree?
This is for what we did on Thursday.
No, I
Cool.
did not.
All right. Sweet. So we're going over the first thing in the lab, which was making sure that our largest value in tree works for negative numbers. And in both cases, Liana and Kevin, if I can summarize, looks like what you did was you made sure that like there was no default value for those left and right maxes. Kevin, you just used recursion. Cool. Into it. Sounds good to me. But just only looking at the values of the nodes in the tree. And so we can make sure we get the actual max. Any questions? Cool. I think that one we went through in full detail. But what I'd like you all to work on, and let me get a sense, do you guys want to pair in breakout rooms or do you want to just work on it all together as one? And by that I mean you four without me. On the question or on the task to swap all leaves in a tree. So from a parent node of the leaves, swap all of the leaves in a tree. Pairs or quad?
Have you talked to your parents about that you need to upload photo stars?
We started by asking if the nodes we were located at were leaves or not.
Okay. 1, 2, see. We are leaves.
Sorry, I had classes too, and then it went over.
Okay. Why did you do that?
Is it over though?
Because it was needed.
Okay.
Basically, if it's not leaves, we can't swap them. So we need to make sure we're at the lowest possible level.
Cool.
Oh, like you were doing.
So I'm going to say we'll need to check the lowest possible level. Good. Okay. What else? What are some other thoughts or approaches?
One of the concerns that I have was how we're storing this and returning this. Like what all that's gonna, like what do we need to store that in and what are we returning? Yeah, type.
Cool. So let's say our function signature. Oh, let's see. Oh, that's right. Swap leaves. Is this gonna return anything?
Okay, so math, ELA, and
I would say no, because we're just mutating a tree.
Cool. So we are not returning because we're just mutating a tree. Does this need the mutating keyword?
No, I don't think so.
Why not?
Because we're just it's on the outside of a function.
We're just changing something outside the function. It's something a little more fundamentally Swifty.
It's not a struct, it's a class
Yeah,
that we're working with.
that's correct. And again, why were we working with a class?
no.
Or why do we implement it as a class? because left and right refer to items of the same kind. So if you remember, we get a big old stinky error. Do this. Structs do not allow us to set as a stored property something of that type. And similarly, classes don't use the mutating keyword. Cool. Sounds good so far. So to Tia's question, there's no returning, we're just changing something. And then how are we storing something? Well, the nice thing is going to be that because we actually have an instance of a binary tree node, we can just change self, right? To store the changes, we can just change self. But how are we going to do that? Let me ask, did you guys try to do this recursively?
Yeah.
Okay. What might be difficult about doing this recursively?
There is no
Go ahead.
no, finish your question.
What might be difficult about calling this recursively inside the function?
It doesn't return anything.
Yeah. The thing is, we don't actually want to return anything. We can use recursion. Also use recursion until we reach a base case and say to stop. So, for example, we could have guard, this thing is correct, else, and then with any function that returns void, we can just say return. We do this all the time in closures in our view controllers, right? So we can just say stop the function here. That's all returning does when you have a void return type. Sweet. Okay. So we're not returning, but we are going to set a base case. Base case. So the Tia and Liana approach was see if we're at the leaf. Sam and Kevin, did you have the same approach or were you thinking something different?
A
I'm sorry?
little different.
Okay. You want to tell us?
Yeah. Go to the node that's right before the leaves. So we check if root.left and root.right is a leaf. If they are, then we swap them. A function I made outside of the swap leaves function. And if root.left is not equal to nil, return swap leaves. So make a recursive call and then the same on the right.
Okay. So if left is not a leaf, recursively call it on left, right is not a leaf, recursively call it. Sweet. So let me steal my leaf diagram here from before. You guys getting sick of this? Because it's a nice tree, but I don't know if you like it anymore. So Sam, what was your base case?
If we reach the leaves,
Okay. So maybe there are multiple base cases. Like I said, our base case is saying to stop. So a base case here could be if, I don't know, children of this node are both leaves. Right? These are functionally equivalent because Tia and Liana, what you're saying is let's go to the leaves. Sam and Kevin, you're saying let's go one step before the leaves. Logically, we just need to be looking at left and right to see if they are leaves. What I'd probably recommend is, what I'd probably recommend is going one step before you're at the leaves, checking if they are the leaves, so that you can stop it there and swap them. Because otherwise, with this approach, which you could definitely make work, but we might run into the issue where all children get swapped rather than just the leaves. So for example, if I am at this level, it's a little difficult to swap 4 and 5 on this node if I'm looking at 4, because I might not know, think of it like a linked list, I might not know who the parent for 4 is unless I include some information. But if I look at 2, and I say, is 2.left a leaf and 2.right a leaf? If so, swap them. Then it's going to be easier. And if they're both leaves, I can say swap them and then stop. So I can do that all in that guard statement. Cool. Who wants to do this thing? Guard self.is leaf. Let's make sure we're not a leaf. But if we are, what should we do?
return.
Yeah, it seems like a good point to stop. So the reason we would still include this is, what if I had a node, let my lonely node equal binary tree node taking in 3. And I said my lonely node dot swap leaves. There's absolutely nothing to do here. So there is one edge case where I want to just say, hey, if you happen to be given a leaf to do this recursively on, just make sure you stop. Stop right away. So one base case is calling this on a leaf. What else do we need to check?
Do we want to check if left is a leaf and right is a leaf?
So guard to make sure. So here's what it looks like, and I hate this stuff, but if self.left.is leaf and self.right.is leaf. What are we doing there?
Swap them,
Yep.
swap the values.
And why doesn't this work right now? It's a very Swifty reason.
They're still optional.
Yep, they're optional. So we can't use is leaf as a conditional right here. But we can say that. Is that what we want though? This is what it suggested. Is that what we're looking for, or what is this evaluating?
Not checking if they're leaves, it's checking if they're not no.
Yep. Cool. So what do we actually want to do?
Would you have to nest the if statements? Like if root that left is not nil, and if that left is a leaf, then swap.
Well, let's see if we can do something else.
If left equals, never mind.
Oh, keep going.
Just optionally binding them on the same line.
Yeah. So we could do, let me comment this out. If let left leafiness equal self dot left dot is leaf, where left leafiness will equal to true, right? Because we got to unwrap it and then compare, and do the same for right leafiness self dot right dot is leaf, where right leafiness is double equal to true. So we could optionally unwrap. What's it going to yell at us for? Okay. Sorry, I'm writing in Swift 2. We could do all that, but the nice thing about our optional is if there is optional dot sum, aka is a value, we can do a direct comparison. Remember, an optional is just enum. Come on, dude, let me do this. Optionals, they're amazing. So just to hammer that home, code preference that we don't need to optional bind, we should not. Yay, there's something to learn all the time. Does anyone want me to explain that before we keep going? Can anyone guess at why before we go on?
I want to make sure that they're both leaves if we want to swap them.
Yeah, sorry, the why here being, why wouldn't we optional bind?
Is it because they would be different from what we're actually trying to do? So we'd be like swapping different values?
The values will be the same.
I mean, we'd be swapping.
Go ahead.
We'd be swapping like that left is equal to self.left. We'd be swapping those new variables we create.
Yeah, so that's the super important thing here is when we use optional binding, we actually allocate more space for this constant right here. So left leafiness would be something saved in memory somewhere else than actually self.leaf self.leaf. So that node, this bool would be saved somewhere else. So if we only need to check some condition, then we should probably not optionally bind it. We should optionally bind, or let's say use optional binding if we need that value in the scope, but we don't need that value here. Cool. All right. This is a really fun base case. I know you're all really enjoying it. So let's go back to what we're trying to do here. If both children are leaves, what should we do?
Swap them?
Yeah. So can I just do this? And remember, actually don't need self for properties. Does this work?
No.
Why doesn't it work?
You're trying to get the value. Right? Or are you swapping the entire node?
I'm just going to swap the nodes because I think that would be easier. So if you remember our, go ahead.
I mean, you can't do what you just did right there because left now equals right. So you're just setting right to what it already is.
Yeah. So we lose the value of left here. What can we do to make sure we have that value?
Maybe put it in something else.
Put it in something else. Here. Tia, how would you recommend doing that?
Just creating variables to put that stuff in.
Oh, go for it.
Swapped leaf, swapped left, or something like that.
Cool.
No.
Like that.
I mean, no, just swap it from the door, right?
I'm sorry?
So var swap left can be right. And we're not going to lose the values of left and right.
So like this.
Yep.
And
then var swap right is equal to left. And then get rid of the stuff underneath it.
So like that.
Yes.
Okay. Let me ask, is this actually going to mutate a tree?
No, we just want to make sure that we have something to store the swap variables in before you put it in so that you don't lose or reassign what left and right is.
Okay, so what should we do next then? So I think we could just do something like this, actually. And just as like a DSA kind of thing, we probably only need one of these things. This is like a pattern you'll see a million times. Using a temporary variable only need to store the first value that's going to be something like, if I say I've got this temp, which is the right, the very next line is where I would replace the value there. So if I say, hey, I'm gonna overwrite right, let me just stash the value so that when I go to change the other thing, I can just use that stashed value. So it's so hard to like put that into a unit, but this is a super important just like programming thing. If you're gonna swap two values, a really easy way to do it is to say, let me hold on to the value of the first thing that I'm gonna change. Let me change that with whatever I'm swapping it with. And then that thing that I'm swapping it with, I'll use that temporary variable, or I guess it could be a constant here because we're not changing it. Let me make sure I have that stored so that later I can replace it. See this all the time.
Is that to save on space complexity?
Well, it's actually like, if I don't have this, I'm just, like you said, losing a value.
No, I understand that, opposed to the first way that Tia did it.
Oh yeah, yeah, exactly. So like, if you think about kind of like the algebra of it, you only need to stash one of the values because the other one you're just using directly.
Mhm.
Sam had an outside func for this logic. Cool, what is it? Something like this. Work. Thanks, Sam.
David, I think I just got it.
Uh-oh. Uh-huh.
He's got it.
Oops. I'm gonna put it in Slack.
Your turn. I love that. Yeah, let's take a look.
1 second.
Sweet. So we hit some base cases. If we're at a leaf, if both children are leaves, and then if we have a left, now think about the rest of it, right? The nice thing about a tree is that there are kind of only 4 cases. There are no children, there are 2 children, there's a child to the left, or there's a child to the right. So we can just recursively, for those last 2 cases, go ahead and do it. So if the root, which is self here, left is not equal to nil, then what should we do?
Call it again using the left.
Yep. But here's the thing about my recursive function. How am I going to get this to work? I want to say swap leaves.
Don't you need a parameter? So you want to keep changing what the root is on this?
So I want to
So
keep
I would-
using what the root is. Yeah, go ahead.
So I would think that you would want a parameter that takes in a root.
Say I didn't have a parameter at all though,
Okay.
because we're inside of a class definition, right? So consider this behavior that any node can do. And as a hint, think about this. So if left exists, then I can just say, call this for left. Right exists, I can just say, swap the leaves for right. How do we feel about that? Again, remember, think about this, instead of as some standalone function, we're in the class binary tree node. So we have properties left, right, is leaf, and instance methods, swap leaves, and a private func swap nodes that works on an instance. So because left and right are of the same type as the scope of whatever I'm using, I can use those same functions on them. So this is recursive inside of the class definition. How do you feel about that? Sam, do you like or dislike recursion more today? Likes it today. That's great. I'm glad to hear. Okay. So if we condense this all down, it's only 7 lines. We see if we're at a leaf and we say do nothing, what am I missing here? If the 2 children are leaves, I say swap nodes, but what should I make sure to do? If this is one of those base cases.
Return.
Yes. Make sure we return after we do it so that these don't get executed. Oop. And actually, this would work just fine, but it's okay. Cool. And then if one is not a leaf, we can do this independently, because now that we're at a specific node, if left exists, go ahead and do this all the way down the left chain. If right exists, do it down the right chain. At this point, we don't care about left and right as siblings anymore. So if this node is the parent, left and right are its children, so left and right are siblings. We don't really care about them as siblings because these functions can work independently. So we already handled all that other stuff up here. Should we spend like 3 more weeks on trees?
Definitely not.
I'd rather get it.
What?
I'd like to understand them.
Yeah, well, I can definitely keep putting out questions. And I want to encourage you guys to come to office hours. It doesn't just have to be to reassess. We can just talk about code if you want the one-on-one time.
Y'all must not be doing your office hours with David because you're mentioning it all the time.
What?
You mention the office hours all the time. They must not be going.
Well, I block out like 8 hours a week and just kind of sit there sometimes. So help me with my boredom, if nothing else.
You'll regret saying that.
Okay, thanks. Cool. So the last thing I want us to work on, and I'm going to have you all split out just for 25 minutes again. Breadth first search. Instead of searching down the chain of each tree, instead of going depth-wise, it hits each node at each level before going to the next level. So with this tree right here, we would look at the numbers 1, then 2, then 3, then 4, 5, 6, and 7. Whereas depth first search, we go 1, 2, 4, 5, 3, 6, 7. So remember, the recursive call will execute all the way down the left before it goes to the right. And everything we've been doing, by the way, is kind of just searching. The search is kind of nebulous, but we could be searching for anything. We could be searching for the number of levels. We could be searching for a specific value. We could be traversing just so we can swap things. Those are all kind of in the context of searching. So for a breadth first search, we can do the same kind of stuff. This is going to feel more iterative, and it's going to use a queue. So we'll queue up. Let's make a queue. Queue can take in any type. Let's make that comparable. And here, our queue is literally going to be queue to queue up binary nodes. So binary tree nodes. So the nice thing about our T here is that it can include, because it's generic, our binary tree node. However, in order to make this specific implementation work, what needs to be true of our binary tree node? If I want to be able to make a queue of binary tree nodes, why doesn't this work?
It needs to be comparable.
Yes. So our binary tree node needs to be comparable. How do we make that work? Now let's get some stubs. Cool. Remember, all our nodes do is they store a value. So here's the really simple implementation of less than and double equal. So because our tree node takes in a generic comparable type, we really just want to be comparing those values because that's the only info that it holds, right? And so to do that, well, any T that's comparable, let's just compare that value for a binary tree node. So if I have a node with value 7, that's going to be node with value 8. It's going to be smaller than that. We're just going to look at the value. So now that that's set up, let's see if we can queue it up. What else do I need here?
A type.
We need a type. Cool. So I could do that here. That sounds nice. But is that going to work?
Doesn't it need to know what its type is if you're assigning it to a variable or a constant?
Yep. There's something else going on here too. You can't use generics as any in the global scope. So if you think about this, when it's actually declared, this isn't the definition. Generics go in our definitions. This needs to be a concrete type, or at least a protocol, an existential type. So what that means is we could either change the type of this, or ultimately where we're going to use this Q is in our breadth first search. So I'm just going to put this right here. Func breadth first search for value T. Put our Q in here. So var Q is equal to a Q that takes in binary tree nodes that have the generic that's defined way up here. So T, because we're in the scope of the class definition of binary tree node, T is whatever type we actually initialize our binary trees as. But the generic T for Q, this is wonderful. That generic T for Q is a binary tree node. So Q in this definition is not taking a generic, but our binary tree node is taking a generic. Cool. And what we're going to do is we'll look at the node and then queue up its children. And this is where you all take it here. If you want, I will paste into Slack a good implementation for a queue. But what I'd like you all to do is from here, treat this as like an iterative search. Whereas before we were using recursion, here you want to iterate through. And the hint is iterate until the queue is empty. Queue dot is empty. Cool. So let's go back in breakout rooms. I'll paste this function and I will paste a queue implementation for you to use. You can just use that right out of the box. And let's spend the rest of the time going over this. Any questions before we go into breakout rooms?
Can you ask that again? Sorry.
Yeah, how do we do this step right here? We've got a queue. We got to see if it's empty. How do we add the first item's children?
Q dot NQ, left and right.
What do we need to make sure before we actually enqueue it?
If it has children, so if it's a leaf or not. If it's not a leaf,
So if it's a leaf, sorry.
no, yeah. I keep getting mixed up about the is leaf, but if it is a leaf, that means it has no kids.
Mhm.
Then you can DQ, and then we'll have to return to the rest of the stuff in the queue.
DQ. Look at next. Cool. Okay. Let's do this. What will we do otherwise?
If it's not a leaf, then we have to go down another and look at the kids and put them in the queue.
Cool. So if left, and then this is the step why we would want it to be in a tree. And that's because we just have self here when we're talking about a tree node. So what we'll want to do is something really janky. We'll say something like var current node is equal to self. Then we could say if current node, sorry, let me do that again. What we have to do first is make sure that there is some node to look at inside of here. So before we even get in there, we want to enqueue self to make sure there's a node that gets into this while loop. If Q lets us peek, forgot how my Q works, sorry. If Q lets us peek, that's because this isn't empty. And if peek is double equal to the value, then we stop, we found the thing. But if not, we enqueue nodes children, like we said there. Which child, I'm sorry, which node are we looking at? How do we get access to that?
It's the one in the queue.
That's right. And what's the only way to like get something out of the queue?
To get it out of the queue?
It's not a pop, is it?
DQ.
It's DQ. Cool.
Oh yeah, no, I need that.
So we'll DQ something. Let's say current node is equal to q.dq. And then this makes it much easier because we're just looking at a node rather than looking at the queue itself. Hi, Levi. So now we don't have to worry about manipulating values in the queue, but instead we'll just use the queue as something that gets and gives nodes. Make sure I'm using functions. So if I've enqueued self here, which would be the root, then while my queue is not empty, I'll grab the first thing. And I think that returns optional because we love Swift. Yep. So I'm going to put a bang on it just because we know there's something there. Then if current node's value is equal to the value we're looking at, so some t that's comparable, then we found it. That's pretty cool. If not, we can do some stuff in order. We can say if current node left is not equal to nil, q.enqueue current node dot left. We can say the right, same for right. Current node dot right is not equal to nil. Q.enqueue node right. And I'm being lazy here and using the bang because specifically I don't want to create a new instance of a node here. I'm not using optional binding because I'm feeling lazy. If I know there's something to the right, I'll just put that thing in instead of saving its value. Then here is the thing. That's kind of all we need to do. Why is that all we need to do?
You're NQing and DQing and looking through each value till you find it.
And if we don't find it, how does it terminate?
The queue is empty.
That's right. So we'll exit this loop. And then let me check my thingies. Got that. Print May. Oh, I hate this editor. Yeah, to answer your question, that's why. It's because I hate this editor. But let's run it, see if it works. Uh-oh. Got a warning. Oh, it doesn't let us have implicit return. Okay, so for our comparable here, we got link list node, queue node, and then here we have to return this. It's with 5. Then on 55, we return, great. Cool. So now we didn't use it. Let's let this, thank you for the helpful hint. All right, so if our breadth first search is gonna work, we gotta construct a tree. Let me just steal it from my Xcode. Hey, node. Cool. Cool. Those guys. Then we need to connect them by setting left and right. Got those guys. Great. And now because this is an instance method, if we're gonna breadth first search for, let me just make this underscore. We're gonna breadth first search, then I have to call it as an instance method. That's why I said it would probably be better to just have this as a instance method in a tree class. Are you ready to see what happens? All the magic, it's amazing. It found it. Kevin, it found it.
Yay.
Do you think it's gonna find 41 though?
No.
Dang. Cool. So trees are really just these very simple structures that either have 0 things or 2 things or only 1 thing to the left or only 1 thing to the right. And so when we're manipulating them, it's just a matter of thinking about each node and then only thinking about those 4 cases. Is there anything there? Are there 2 things there? Is there a left thing or is there a right thing? That's our binary tree. And that's why it's so simple and that's why it's so easy. And that's why a lot of operations end up with log of n complexity. I know this is amazing.